Hello, everyone, and welcome to the Vision Seminar. It's a pleasure to have today Professor Olga Russakovsky to talk about fairness in visual recognition. Dr. Olga Russakovsky is an assistant professor in the computer science department of Princeton University, where she focuses on computer vision and its intersection with machine learning, human-computer interaction, fairness and accountability, and transparency. She completed her PhD at Stanford University in 2015 and did a postdoc at CMU in 2017. And Olga has done a lot of groundbreaking work in many areas of computer vision, for which she has been awarded many awards. Amongst others, she was the lead of the ImageNet Large-Scale Visual Recognition Challenge, which has served for many years as the main benchmark for image recognition. And it was a work that, having been cited over 17,000 times, allowed to train and evaluate models with lots of data, which probably kickstarted deep learning in computer vision. Amongst others, she was named one of 35 under 35 innovators by the MIT Tech Review. She got the PAMI Everingham Prize in 2016, and she recently has been awarded the Anita Borg's Emerging Leader Abie Award in honor of Denice Denton, and the Anita Borg Early Career Award. On top of all of that and all of her research, she is really committed in multiple initiatives promoting diversity and outreach in AI, and she is the co-founder of AI for All, which is a foundation dedicated to educate diverse future artificial intelligence leaders. Welcome, Olga. It's a pleasure to have you here.
Awesome. Thank you so much. That was a great introduction. I'm very flattered. Thank you. Let me share my screen. So this worked before, but of course will probably not work. Oh, no, it worked again. It's cool. So I'll say, before diving in, so I know that for various reasons, video is turned off for many people. If you are in a space where you feel like you can turn on video and you, feel safe and comfortable doing that, I would certainly appreciate that. It's a little bit more fun to be able to actually see folks while talking, but I also understand, for variety of reasons, this may not be an option that's available or comfortable and so on to you. So, right, thanks for having me. So let's talk about fairness in visual recognition. So before I dive in, I'll say that I'll talk about sort of 4 different lines of work, some more briefly than others, and the lead authors are shown here. So this is Vikram Ramaswamy, Angelina Wang, Zayu Wang, and Kaiyu Yang. So let's start with a grounding example. So in 2017, among several other examples of computer vision doing crazy things, one of the prominent examples was a computer vision model that learned to increase attractiveness of a photograph by manipulating its skin color. So I'm going to put aside the issue for a second of why somebody felt the need to design a filter on a photo app that increased attractiveness in the first place. So that's already problematic, but sort of putting that aside, it turned out that what this system did is learn to correlate increasing attractiveness with manipulating skin color. And since then, there was a lot of questions about, sort of why this happens and how could the creators do something like this, and sort of how should we be thinking about this, be preventing these kinds of issues and respond to them. And there's kind of a simple answer to this, which is essentially to shame the app creators, and they certainly deserve some amount of it. There's also
blue goat.
Oh, sorry, could you mute, please? I'm hearing somebody else. Thank you. But there's also sort of a deeper set of issues here, right? So where we have some biases, prejudices, stereotypes that form part of our history that then makes its way into large-scale data, sometimes unbeknownst to us, which makes its way into AI models, ultimately then makes its way into AI decision-making, and that actually becomes part of our history again, sort of completes this cycle. And so the question that we want to ask, in addition to sort of calling out, individual instances of problematic technology that gets built, is at a higher level, can we think about ways to adjust the AI design to try to mitigate some of these effects? And I note the word mitigate rather than remove. This is not going to be something that we can remove entirely, because essentially the only way to remove it is to sever some of these connections, and that is unlikely to happen. But we can talk about how to mitigate some of these and prevent some of these particularly negative outcomes. And so let's start by talking about specifically the data side, and I'll get to the model in the second half of the talk. But on the data side, the key message, right, which chances are many of you have heard already, is the fact that large-scale data does not necessarily mean fair representation. And this can come in many different ways. So one of the possibly best known examples is in face recognition and in face recognition data sets. So Joy Blamwini and Anita pointed out in 2018 in a very influential paper that face recognition technology tends to be more accurate on faces with lighter skin, and they linked this to the fact that in dominant face recognition data sets these days, these data sets tend to have predominantly white or light skin training examples, and so and by predominantly I mean 80 to 90% of the images. And in this case, there was, they proposed a relatively straightforward solution, right? So if different skin colors are underrepresented, what do? You can go ahead and collect more examples. And here, this is clearly, an issue of underrepresentation in the data set. This doesn't, the statistics of the data set here don't reflect statistics in the real world. It's just an oversight on the part of data set creators. And so the solution is fairly straightforward. There's more and more complex issues that are starting to be revealed, such as the issue of geographic diversity in data sets. So this is a paper from 2017 that pointed out that in large-scale data sets like ImageNet or Open Images, there is a distinct lack of geographic diversity. So primarily the images come from the US, a little bit from Canada, so America, right, Australia, Europe, but there's also large parts of, for example, essentially the entire continent of Africa is not represented in these data sets. And here, I'll give a few examples later, but essentially you run into issues even with something like object recognition, where the same object may actually appear very differently in different countries. And so when you're training a model, it's important to be aware of the fact that actually you're not training a completely, you're not training a model of this object that is true across the world. You're really training a model of what this object looks like in essentially the US. So here, when you start talking about how do we mitigate these issues, this becomes much more difficult. So you're starting to talk about things like, what search engines are you using and what languages are you doing the queries in, and what happens to folks who may not have access to the web, what happens in countries where people don't have the same culture of like uploading their photographs to social media and so on. So the solutions become much more complicated. Speaking of search engines, right, there's also a line of work that talks about the representation. So we frequently use search queries to get images for our data sets, and this has been the dominant paradigm now for many years. This is the cheapest source of data. And so you query for example, a term like CEO, you get back a bunch of pictures from the web. And there's been multiple studies, this is one of the first one in 2015, but multiple studies that sort of talk about whether the images that get returned by search engines are actually diverse and representative. So here, for example, you can see when you search for CEO, what do you get? Predominantly white men in suits. And this is actually more diverse because this is a search that I did about a year ago myself. And this is actually, the results were more diverse than what the authors observed back in 2015, partially because the fact that this paper came out influenced the way Google then returns search results. But this is, again, not a simple problem to solve, because ultimately the job of the search engines is to reveal the most distinctive examples of the search query. And it's actually not to return a diversity of examples in a way that makes it easy for computer vision dataset creators, for example. And so there's kind of this imbalance in objectives that we kind of have to grapple with, right? If we want to use this as a source of cheap data, we're going to have to grapple with these issues that the images that are going to be returned here are not going to be perhaps as diverse as we would like them to be. And finally, the last bit that I wanted to highlight, which is, again, going sort of one level deeper, is that there may be stereotype representation within a data set of, for example, of different genders. And so this goes beyond statistics. So for example, here, these are examples from open images. These are, the top row is example images where the person in the image is labeled as female. The bottom is images where the person is labeled as male. And these are examples of images that have flowers in them. And so the statistics of how many times do females correlate with flowers versus males correlate with flowers, the statistics are actually quite similar. It seems like there is plenty of examples of both genders with flowers, but if you look at the actual examples and the actual images, obviously the type of images that are very different. And so the portrayal of the two different genders is very different. Even those sort of statistics and the kinds of counts that we might be used to computing on these data sets sort of say otherwise. And so with that, we'll dive into a couple of pieces of work that we've done trying to sort of think about ways to address bias or underrepresentation or stereotype representation in data sets. And so the first one is more on the side of sort of thinking about how do we counteract disparities in the statistics and the counts. So here, for example, we are annotating demographics on 139 people synsets or categories within ImageNet. So ImageNet, large-scale data set, a bunch of categories illustrated with images from the web. These are a set of synsets of different people categories, and we're annotating gender, statistics, skin color, and age. Annotations aren't perfect, but we can at least get some sense of the relative distributions. So some examples in here. So for example, you can see in the gender category, there's one synset where the workers are very unsure. So this is actually scuba diver. They're legitimately unsure because the person is wearing a scuba suit. But across the others, you can see that kind of as expected, right? So predominantly the images are male, predominantly the images are people of light skin, and predominantly they're adults 18 to sort of young adults in the 18 to 40 range. And so what can you do with these kinds of annotations? So for example, you can rebalance your data set, right? So now that you know that, for example, for the synset programmer, you have predominantly men with computers, right? So you can rebalance, for example, across gender. You can say, I want an equal number of men and women represented in the data set. And by the way, so I'm making, you know, several simplifying assumptions, and will be throughout the presentation. So one being of binary gender, which is, I know, a simplifying assumption, but this is sort of a cost of doing business at this time where we're, you know, we need to make some kinds of, this is why we actually introduced unsures, to try to capture sort of the cases where this may not be a valid simplification. And I'm talking here about annotated gender expression, right, which may be very different than gender identity. Now, so what is the problem with these kinds of this kind of approach, right? So, or rather, right? So I call them subtleties, which maybe is a better way of thinking about it. So this is not necessarily a problem, but it's a subtlety we want to be aware of, right? So what does rebalancing mean? It ultimately means we're removing the data, right? So is that the best thing to do? Maybe, maybe not, right? So we are essentially saying that we're going to get some data, but then we're throwing some of it away in the from the data set. This also means we're changing the original distribution, right? So there's some kind of real world distribution. Then there's some kind of distribution that we're able to get within the data set using this data collection process. And now we're further altering that by modifying in some way and enforcing some kind of assumptions about uniformity. Second, of course, is the question of accuracy and validity of these labels. And I've sort of alluded to this as well, right? So these are somebody going ahead and annotating, you know, this is annotated using Mechanical Turk, and sort of crowd workers making some kind of decisions which may not be correct. There's, of course, very important questions about the implications of including people categories in a data set. And so if you're interested in that discussion, so we tackle this a little bit in the FatStar paper, so that published this, is just talking about, why is it okay, and is it okay, and what kind of sort of people categories would we want to include in a data set, and which ones are not acceptable to include. And related to this also is the issue of privacy and consent. So you may notice that many of these sets have examples of children or minors. What does that mean to be including them in a data set? And also the questions of consent of content creators. And so this is a paper that we're actually working on now, sort of grappling with some of these issues and trying to sort of think about what would be constructive solutions going forward, balancing the realities of the need for large-scale data to advance computer vision, which will ultimately have a variety of benefits for across a variety of applications and potentially, life-saving applications, versus again, some of the realities of like, what does it mean to collect data sets the way we're collecting now, which is essentially anybody who posts a picture on the web, we're assuming implicit consent to be included in the data set. And finally, right, so the last piece, which I already mentioned, is the representation of folks of different genders or skin colors or ages within a category. And so actually within the programmer sense, one of the things we notice is even after rebalancing for gender, a lot of the images of men with of men in that sense that were men sort of sitting in front of a computer writing code themselves, and a lot of the images of women were actually occurring together with a man in a photograph, and were looking over the man's shoulder while he was writing code, or there would be a woman writing code, but there would be a man looking over her shoulder sort of explaining something. And so this got us thinking about the question of representation in a data set. And this then led to the creation of the REVISE tool. So REVISE stands for Revealing Visual Biases, which I know is not a great acronym. It was initially called VIBE, which was Visual Image Bias, Visual Bias Extractor. But it turns out at CVPR, there were 2 other papers with the acronym VIBE, so we had to quickly change it. So it's now called REVISE. And this is appearing at ECCV next week. And so this is a tool for taking as an input a visual data set and whatever annotations are available, and outputting a set of metrics and also some possible insights and possible actions around how do we think about fairness and representation in this data set. And so I'll go into quite a bit more detail about REVISE, but the key contributions are as follows, right? So we're going beyond underrepresentation to actually analyzing differences in portrayal. It allows for semi-automatic analysis of large-scale data sets. And so semi-automatic because really fairness will ultimately require manual intervention. So it's very hard to extract statistics, so we can extract automatically statistics from large-scale data sets and sort of show them to the user and say, I've discovered the following pattern, but then it's ultimately up to the dataset creator or user to determine whether this pattern is actually completely reasonable, reflective of real-world patterns, perhaps not harmful, or if it's problematic and something that they want to fix. And doing this automatically is definitely a much more complicated problem than we can solve, but we're able to at least compute a bunch of these statistics and make it possible in data sets which are not, where we're not going to be able to analyze them all manually, at least to sort of focus the user's attention on some particular aspects of it. And so finally, the goal, right, is to integrate sort of this idea of bias mitigation throughout the dataset construction process. So rather than I constructed the dataset, I trained the model, I released it into the world. Oh, oops, my model is racist. Who would have thought? Now you can kind of do this analysis along the way and think about what's actually in the data. And so, oh, I forgot to change the name. Yes, this is still the VIBE name, but. So the implementation, so this is freely available Python notebooks. This is one of the design decisions that we made, is that this is going to be in the form of Python notebooks because our target audience is really computer vision data set collectors. And so we're talking about, how to improve the user interface, but it's actually not a top priority for us because we think that the main audience is folks who would be, already writing Python scripts to collect the data, and so they can. It's actually better to give them access to the inner working of the tool and just in the form of Python code. So we're analyzing portrayal of objects, people, and geographic regions within the data set, and using provided annotations, whatever annotations are available with the data set, as well as pre-trained models, as well as some models that we're training on the fly on the data, fairly straightforward models. And so in this talk specifically, so I'll talk about portrayal of different genders. So I'll sort of omit the objects, which are where a lot of the statistics we implemented are actually sort of more in line with what's been done previously. And so this analyzes, object scale and number of different objects of different categories and so on. So it's sort of things you would expect. And we'll, between the people and genders and geographic regions, I'll just focus on one of them, which is the genders. Again, caveat as before, so we're using binary socially perceived gender expression. The analysis is done on COCO and open images, although we've since then run it on an image and object detection data set, and are also sort of looking at several others, and are trying to make sure that the tool is extensible to whatever data set you want to run it on. And the gender annotations here are derived from image captions following prior work. So let's look first at the first set of statistics. So this is co-occurrence of males and females with different objects and in different scenes. So the analysis here is we're correlating the presence of different genders in COCO with object categories and with scenes. So let's talk about object categories first. So we're using ground truth object annotations grouped manually into super categories. And so object category is on the left, such as sports vehicles, outdoor, kitchen, etc. On the x-axis is the fraction of images that contain this category. And this is again broken up across images of males and females. And so we can see kind of as expected, right? So sports objects are primarily correlated with male, kitchen objects primarily correlated with female, so as expected. For scene categories, so we don't have scene category labels, so we're using the pre-trained places network. We're using the 16 intermediate categories rather than the full set of 256 categories. And so again, here kind of as expected, we are seeing that outdoor sports fields and parks are correlated with male, shopping and dining correlated with female. And so the tool would sort of return these kinds of these plots and potentially highlight again some of the places where one gender is particularly overrepresented and underrepresented. So this is the more sort of straightforward, right, correlations with different objects with different scenes. Right, and so the actionable insights here would be, for example, to collect images of the underrepresented gender with the corresponding object or scene, if that is in line with what the dataset creator intended. So the second thing we're looking at is kind of thinking back to the thing I mentioned in the programmer example, right, is whether a person just appears in a photograph together with, an object like a computer, or whether they're actually interacting with it. And so here we're using person-object distance as a proxy for interaction. We're relying on bounding box annotations in the data set. And so here, for example, the musical instrument organ is one of the ones we've identified as having a difference across the two genders. So what do? So across all images, we have the bounding box for organ, we have the bounding box for the person, and we have the gender labels, right? So male or female, and we can measure the distance between the two bounding box normalized by the bounding box size. And so here, for example, we find that while again the statistics of the co-occurrence statistics may be similar, but in fact female tend to occur much further away from organs than men, right? So which and we've done some validation, but again, distance tends to be a reasonable. It's not a perfect proxy, obviously, for interaction, but tends to be reasonable. And so the actionable insight, right, is consider equalizing the level of interaction with the object if warranted. So think about, particularly querying for women playing organ, for example, again, if that's warranted. So the third piece is the one I keep coming back to. So there's differences of portrayal of different genders. And so here the analysis is for each object class. You can learn a visual classifier for recognizing this object when it's present with female versus present with males. And so here we're just running a classifier on the positive examples, which makes it a little bit easier and more tractable computationally. And then we're trying to identify classes with the most stark differences between genders. And so one of the examples was flowers, which I already, it's actually very easy to classify images of flowers as whether they've occurred with women versus men because of this. So you get sort of these patterns where the female examples are more sort of stereotyped and stylized images, and the male examples tend to be men in conference rooms with flowers. And this is also true, for example, for sports uniforms. So this is actually, it's either COCO or open images. I'm blanking on which one, but I think this actually was potentially true in both of them, because I remember this kept coming up. Is the object of sports uniform, right? So again, very different representations for women and men. And so, again, the actionable insight would be to collect more images of each gender with the particular object in more diverse situations. And so finally, this is the last bit of analysis, was actually around the gender labels themselves. So we were looking at whether the occurrences where gender is annotated, but the person is either too small or no face is detected in the image. And our hypothesis was that on those examples, gender actually should not have been annotated. So if you can't detect the face, or if the person is very small in the image, you actually should not have a gender label assigned to it. And it turns out that, in fact, in the majority of those cases, the label in cases where the label was assigned on these images, the label defaulted to male. So for example, you have images like this where arguably you actually can't see the person, but nevertheless, again, the labels are extracted from captions, and the captions actually refer to man and boats. It is likely that the people doing the captioning actually are using man here as a proxy for person, but the way we are extracting, the way, again, it's been done in the literature, the way we're extracting the gender labels, this would default to male. And so, the actionable insight right here is that we might want to prune these gender labels. So we might want to verify that actually the gender labels that are, collected or inferred in this data set are actually valid labels. This could be one way to do this. So I will pause here in the sort of first part of talking about the large scale data. So to summarize, right, so we need targeted efforts here to both increase representation, but also examine and understand the data and sort of engage with these issues of underrepresentation in a constructive way, right? So rather than just saying, our data sets, have this particular issue, how do we actually think about, constructive solutions and mitigating some of these? So I'll pause here for a second before I move on to the models, if anybody has any questions.
I do.
Great.
I'm just curious, we're having this discussion around computer vision, but are people having these discussions around search engines? That would seem to be some of the issue.
Yes, absolutely. So there's actually a great book called Algorithms of Oppression by Safiya Noble that actually engages with a lot of the issues of search engine portrayal. In particular, the example she uses is the portrayal of Black girls by search engines, in particular Google. And it's a really great book, a really great study of that. But yeah, absolutely. So people are engaging with these questions of search engines, but I think there is part of that discussion, actually, I think, and part of the reason why we're writing a paper about this is I think that discussion sometimes misses the fact that we can't, it's very hard for us as computer vision researchers not to use search engines because there's no obvious cheap source of data that we could use. And so our options are kind of limited. And so the solution of, oh, search engines are terrible, let's not use them, is actually not a very practical solution, even though that's actually been frequently sort of pitched in the community as the, or in the fairness discussions as the path forward is like, we should not be using search engines at all. But I think that's not practical.
Thanks.
All right, yeah, sure.
I have a high level question.
Yes.
So it's awesome that you guys have built a tool to like sort of visualize the biases in the data. I'm thinking like, do you think like the next step here would be to like kind of like quantify maybe like representation uncertainty of some sort, saying like, okay, like let's say a search engine is returning like a bunch of results, and or a bunch of results. Each result is like a set, like the one that you showed in the first slide, and you can quantify like which set is like more representative. In some sense, we can train models to say, okay, like I'm like 50% confident that like, you know, compared to like 90% confident that this set is more representative. And search engines can, you know, sort of use this as a factor in like, you know, bringing up searches to people and things like that. Do you think like that's like a possible next step to something like what you guys are presenting here?
Yeah, I think that would be great. And I'm definitely happy to talk afterwards about, you know, potential path forward there. I mean, I think there's something certainly to be said for, you know, fixing up search engines. There's also something to be said for collecting all the data we can, but then being thoughtful in actually how we use it to train models. So I think there's also sort of this issue of like, attempts to make a selection between two different results of search engines. At the end of the day, you're actually you're still throwing away some data.
Got it,
and so so ultimately this actually leads very nicely into the next topic, which is so there's no way to completely debias your data. There will always be issues. There will be issues that will you know, continue being revealed, and then ultimately, if you want your data to be representative of the real world, that's going to have inevitably issues. And so sort of the next set of questions and line of exploration is around, you know, what can we do with this imperfect data? And how do we think about training models on the imperfect data? And so there's been, you know, a lot of the, at least initial effort within fairness was around revisiting many of the existing problems and challenges that we've known about in computer vision for a long time from a fairness perspective, right? So this is things like long tail distributions, learning with constraints, domain adaptation, interpretability of models. And so a lot of these are just sort of being revisited in the, you know, with kind of fairness questions in mind. And I think we're actually starting to be past that and moving a little bit deeper into addressing particular issues related to fairness, but a lot of the literature sort of in the past, I don't know, 3 to 5 years or so has this flavor. And so one concrete example of this is we set out to tackle a problem of teaching a classifier to ignore a known spurious correlation in the data. And so here we are doing a toy illustration on CFAR. And we started with this toy illustration thinking that this would be, you know, a 2-week simple project, and then we'll move on to more complicated things. And we did end up moving on to more complicated things, but it turns out this toy illustration actually was much deeper and more interesting than we initially expected. And so the illustration is the following. So we have a training set which has a skewed distribution between 2 domains, and the 2 domains are color and grayscale. And so we take CFAR, we take the images within CFAR, and we convert some of them to we leave some of them in color, and we convert some of them to grayscale. And we do this in a particular way where for some classes we convert 95% of the images to grayscale, and for other classes we convert 5% of the images to grayscale. And so at training time, we have this skewed distribution, which correlates the class label with the domain, which is color grayscale. You know, the you know, picture to have in mind, right, is you can think about the classes being, for example, different activities, and the color versus grayscale corresponding to different genders. And so it's sort of, you have this protected variable, protected domain of gender, which is correlated with what you want to predict. And so supposing at test time, we're trying to classify images into one of these 10 object classes, and at test time, there's no correlation. So we're trying to evaluate, for example, on all color images. And so, you know, what happens when you train with this data in kind of a straightforward way, you train a baseline classifier with this data? So you're testing again on color images, you're training on skewed data, you get 89% accuracy. And one of the nice things about this particular example is we actually know that, you know, one of the things we could actually intervene manually and remove this correlation by basically taking the skewed data set and turning it all to grayscale. And it turns out that if you do that and you turn them all to grayscale while still evaluating on color images, so you sort of intervene and remove this correlation, you can get up to 93% accuracy. And so, right, so these is two models. The top model has actually seen some color images. The bottom one has never seen a color image. It's trained entirely in grayscale. But the bottom one, because it doesn't have this correlation, is actually performing better. And so sort of the other way of saying this, or to, you know, thinking about why this happens, right, you can visualize a confusion matrix. So this is trained on the skewed distribution. On the left, you have the true labels. Across the top, you have predicted labels. The columns are predicted labels. And so classes that are primarily in color during training, they're in bold, they're the last 5 classes. When at test time, the model sees an example of a class that was primarily in grayscale during training, it now sees it in color. It's actually going to predict it as one of the classes of color. So it's going to use the fact that the image is now in color to actually inform that it must be more likely to be one of the 5 classes that were in color during training, right? So it's sort of as expected, it's learned to correlate the presence of color with one of the 5 object classes. And so we ran a lot of different models and analyses and sort of like, how do you train? And here we're assuming that at training time, we actually know which images are color and grayscale. We have those labels. And so we're like, okay, you know, we can try to train this in an adversarial way. We can try to train this in in sort of different kinds of domain independent ways. And so I'll tell you, you know, I'm not going to go into, you know, the paper has a bunch of, you know, long tables with different training methods and different inference methods and so on, but I'll give you kind of the big takeaways here. So first big takeaway is the domain independent training ended up working the best. And domain independent training essentially says, you know, we have a CNN, we're feeding in an image, we're going to have 2 independent heads, 2 independent softmax classifiers, one that's going to be classifying grayscale images, one that's going to be classifying color images. We're training with standard cross entropy laws, but the 2 classifiers essentially will never see examples of the other domain. And at inference time, we're just going to combine their scores before the softmax. So essentially, we're going to average the 2 decision boundaries. So, right, so you can think about the 2 classifiers on top as being linear classifiers on top of the same feature representation. And so we're essentially just going to average their decision boundaries. So this turned out to work quite well and better than essentially any other thing that we tried. And this works especially well in the presence of high skew. So here on the x-axis, we're showing the level of skew. So I said, you know, we're converting 95% of examples to grayscale in some classes and 5% to others. So this is a skew of 95. And we can plot on the x-axis is the level of skew, and on the y-axis is accuracy. And so as the amount of skew increases, this gap between a baseline model, which is learning to correlate color with the target object, and the domain independent model, which is training the 2 separately, the gap is increasing. And interestingly, actually around about 75% skew, this effect disappears, because it turns out that around, at least on this data, around sort of 75% skew, actually the baseline model can cope with that quite well. Right, and so this is ResNet 18 architecture, and the testing metric here is mean per class per domain accuracy. So we're assuming equal color grayscale distribution between classes at test time. So this is kind of the first thing we observed. So the second thing, coming to the adversarial training, adversarial devising, which is one of the most common methods that's proposed in the literature right now, which is we're going to try to build a system that can classify the object classes, but not be able to classify the domains, right? So classify these into, so we have a 10-way softmax. We're trying to classify the object classes, but then there's also a 2-way softmax that tries to classify the domain, and we enforce some kind of loss function. So for example, here this is uniform confusion loss, but you can actually, we tried several different options. It basically says, you know, the underlying representation should be good enough to classify the classes, but not good enough to classify the domain. And so we were actually, maybe this will be obvious to this group, but it wasn't at all obvious to us. We could not get this to work. So we could not get this to work in a way that maintained high accuracy on the target classes. And after a lot of efforts and attempts and thinking that this is just like us failing to tune hyperparameters and doing a giant grid search of hyperparameters and so on, we finally sort of figured out what is actually happening. So what's going on is, so this is T-SNE plot. So the top is the domain. So red and black are the two domains. The bottom is the object classes. So the 10 different colors represent 10 different object classes. And so on the left is in the present, when there's no adversary. So the object classes tend to be, you know, fairly nicely separated. And the domains tend to be fairly nicely separated. But when you add an adversary, right, so it's going to scramble the domains as expected, but it's also going to scramble the object classes and harm accuracy on the object classes as well. And so it turns out it's very difficult to train a visual representation that can't classify the domain. So visual representations are very powerful, right? So here we're asking it to train a representation that, you know, can't classify, given an image, can't classify whether it's in color or grayscale. If you think about this in the fairness space, right? So training a representation of faces that can't classify race is very difficult, because it turns out if you just take examples of faces and you run simple clustering, what's the first thing that's going to emerge? It's going to be skin color that's going to emerge as you know, if you break it up into two clusters, that's going to be the first cue that emerges. Gender is actually going to be the second cue that emerges out of data set. So it's a very sort of tall order to try to train a representation that's not good enough to classify these arguably very, very discriminative, very distinctive features. So the second issue is that in cases of high correlation between classes and domain, one can actually be inferred from the other during training, right? So if you know that for many of the classes, 95% of the examples are in color, if you can classify the classes, you actually have at least 95% accuracy of being able to classify the domain, right? So if you know that it's one of these 5 classes, you know which domain it is. And so it's sort of like forcing the model to be able to classify these 5 classes, but like there's no way you can then force it. I mean, you can say that it shouldn't have higher accuracy than 95%, but on classifying the domain, but you can't actually enforce anything stronger than that. And so this has actually been discussed with tabular data as well, that sort of these ideas of, oh, I'm just going to remove the gender, you know, feature from my data set hasn't proved. So this idea, it's called fairness through blindness. I'm just not going to give somebody access to the gender label. That actually proves to be misguided in many ways, because frequently many other features can serve as a proxy for gender. And finally, I'll just say, so there's a lot of fairness literature out there that will report equal error rates proudly and talk about how they've equalized error rates and will not report overall accuracy. And so when you're reading a fairness paper, definitely look for overall accuracy of the system, because sometimes, you know, there will be misleading claims that sort of talk, or maybe not misleading claims, but there will sort of be claims about like, this method will equalize error rates, but sometimes that happens basically at the expense of both error rates across both domains going up. And so a bunch of these findings hold in a variety of settings, right? So we're talking about, you know, CFAR grayscale. So this is the color grayscale distribution. So we have baseline. If you try to do adversarial training in kind of the standard way, your accuracy will drop. And if you're doing domain independent, accuracy will go up. We've also tried this with more subtle shifts. So this is CFAR ImageNet, where we're substituting images of similar classes from ImageNet instead of converting them to grayscale. So everything is in color, but it's just, rather than, you know, converting 95% of images to grayscale, we're actually going to throw in examples of those classes from ImageNet. So it's a more subtle domain shift. And finally, CRA-WP, which is the standard, one of the standard fairness benchmarks. So here we're doing multi-label face attribute recognition, and the presence or an appearance of the attribute is correlated with gender. And so the last thing that I'll highlight, and I was hoping to talk in more detail about it, but actually won't, because we're still sort of working on this manuscript, and it's turning out to be more challenging and sort of more interesting than we initially expected, which is this question of, can we generate the data that we need, right? So there's a sense of, you know, we can do all kinds of training with constraints and rebalancing and so forth on the existing data, but there's also these things that are, you know, these GANs, which are great at generating data. And so can we think about ways to actually generate the kind of data that we would want for training these models? And so the core idea here that we're looking at is there's real world data. So for example, you know, and we're trying very hard to avoid using gender as the qualitative example in our work, because it's just particularly when we were working with generated data, it's just really better not to show generated examples that are attempting to manipulate gender expression. And so we're trying to use sort of more innocuous attributes. Like, for example, you know, you're trying to predict the presence of hats, and suppose this is correlated with the presence of glasses. And so we're trying to do this, you know, paired augmentation where within the data set, right, so we're going to preserve, you know, the presence or absence of a head, but then also just do data generation in a way that removes the glasses and thus decorrelates presence of hat with the presence of glasses. And so, you know, the qualitative answer, right? So you're considering a GAN trained on a biased data set of faces where the presence of hats is correlated with the presence of sunglasses. And so if we're moving in the latent space, and by the way, so this has been interestingly shown that so this is for CRA-WP. So prior work has shown that in the latent space of this GAN, a lot of these attributes that one would want to predict are actually linearly separable in the latent space. And so when I'm saying, you know, moving in the latent space towards the towards adding glasses, this is actually, you know, you have literally you can train a linear model latent space and sort of move along that towards adding glasses. So if you're moving directly, you're adding glasses, you're additionally adding a hat because the two are correlated, right? So in contrast, what we're trying to do is move in the direction of adding glasses, but then without actually adding the correlated hat attribute. So sort of moving in the direction where the score for glasses would change from no glasses to glasses, but the score for the hat attribute would stay the same. And so the issue that we're running into now actually is some of these, so for, you know, hat and glasses, this all actually works quite well, and this makes sense. You know, you can do this kind of data generation. The problem is some of these attributes, like for example, there's one attribute called arched eyebrows. So it turns out that the appearance of this attribute and the labels are actually heavily dependent on gender. So the same eyebrows will be, or very similar looking eyebrows will be labeled as arched versus not arched differently depending on the gender of the person. And so there's, we're sort of starting to grapple with these like deep interconnections between the labels of our target attributes and then the gender labels, and sort of thinking about, and again, this is something I'm very happy to talk about in one-on-one meetings, is sort of thinking about how to use how to use GANs for data generation and how to think about the correlations kind of beyond the correlations and the labels themselves, sort of beyond just the appearance. So right. So on the, I'm again very happy to talk more in detail about sort of the technical aspects of the work, but there's one more, actually check the time, perfect. There's one more thing I want to say here. So on the AI model side, right, so there's opportunities to both adapt existing techniques as well as innovate on them. Adversarial biasing is not nearly as effective as is claimed in the literature. And there's, of course, this delicate trade-off between accuracy and fairness. And so one last thing I want to say before I conclude is there's this one final piece of this, right? We can talk about the data, we can talk about the models, and there's also the question of who is actually building these systems. So who's actually translating them into, who's defining what applications we're tackling, and who is deploying these systems, and who's controlling how they're being built and why they're being built, and who is represented at the table when we're doing this. And so the question that we like to ask is, we know that AI is changing the world, and the question is who is changing AI? And so I'll spend one last slide talking about AI for All, which is a nonprofit foundation dedicated to increasing diversity and inclusion in AI. And my all-time favorite quote is from a participant in one of the AI for All programs, who said that until this program, I never thought that people who looked like me could succeed in computer science and AI. And so this is a foundation that we started together with Professor Fei-Fei Li, as well as Dr. Rick Sommer, who is the director of Stanford Pre-Collegiate Studies. Started officially 3 years ago, so we celebrated our third birthday on March 8th, which is International Women's Day of 2020. So far, we've partnered with 16 universities to run summer programs for high school students from underrepresented groups, bringing them to campus, or this summer virtually to campus, to learn about some of the AI work going on and sort of teach them some of the basics, and talk with them about some of the potential benefits of AI to society, and also some of the potential concerns like bias and fairness of these models. We also have a free online open learning platform aimed at high school teachers who may want to teach AI literacy in their classrooms, but may not have AI background. And so this is trying to provide lesson plans that can be executed without necessarily having a lot of AI background yourself, trying to sort of increase access to AI education. And then our summer program alumni have started AI research projects. I actually have one working with me and my lab this summer looking at deep fakes. She's a rising high school senior. Done a bunch of internships, working groups, panels, and clubs while still being in high school or early college. And so we have a blog post if you're curious, talking about some of their accomplishments. And the long-term vision here is to foster a community of diverse leaders in AI, right? So not only bring in a diverse group of people who sort of are learning the basics of AI, but also really help grow them into leaders who are helping shape the field going forward. And so with that, I will conclude. We now have a lab Twitter account, Visual AI Lab, so please follow us. I'm trying to learn how to use Twitter, trying to share some of the news, and then of course AI for All also has a social media presence, and I'm very happy to take questions if we have time, or very happy to answer questions by email and meet with you guys in the afternoon as well. Thank you.
Thank you. This was great. Do people have questions? We have, just 5 minutes.
So I have a question on the adversarial debiasing.
Mm-hmm.
How much of that can you actually do kind of post-training? So, I mean, here in this example you brought, right, you use that during training, but I guess what I'm asking is how disentangled are these attributes? So could you say, well, we first train the whole system using the black and white and the categories, but then you actually identify the pathways that correspond to black and white and just kind of kill them. Is that being done? Does that work, or is it then all too much entangled with each other?
So I think sort of the most straightforward way of doing that, right, is that you actually train them separately, right? So you train them either as, you know, 2 separate heads, or you train, you know, a 20-way softmax, which also works, you know, much better than the baseline, and definitely better than adversarial training, right? So you could actually sort of explicitly train them to be different. Because we were assuming that at training time we have access to these labels, there was sort of less of a need to do this post factum, but I can totally hear you, right? If you have a giant data set where you don't have the domain labels, but then post factum you might have, you know, maybe a small validation set where you have the domain labels, and then yeah, that I think that would be exactly the right thing, as you sort of try to right, identify sort of which parts of the network maybe have learned different have learned these correspondences, and try to decorrelate them at, you know, test time, or using the small validation set.
I also have a question also regarding the domain work. What happens when the number of domains increase? Does this gap between like adversarial domain and training different classifier reviews, or?
You know, it's a great question. We actually haven't tried it with more than 2 domains. That's a great question. I think the issue with the adversarial will still remain, in that I think some of the more recent papers, so there's, for example, one paper that is under review now, but is on archive, sort of came out of Stanford, where they actually observed the exact same thing, and they propose a slightly different variation of the adversarial training that actually gets more the core issues of like correlation between, so they are tackling multiple domains, and they're correlating, they're trying to remove the correlation between the features on the domain, rather than like enforcing that the domain can't be predicted, or try and so there's definitely been work, you know, even since CVPR, trying different adversarial approaches, and those seem more promising, but just like sort of not that this is part of the idea around like, maybe it's not just about adapting the existing tools in the setting, but actually we need to be thinking a little bit more about like, what does it actually mean to tackle these particular issues, instead of just like throwing adversarial training at it like we know how to do in other settings.
Yeah.
Hi, I have one question. When we try to mitigate the bias from a data set, so should we try to do it in a joint way, or should we try to do it in a marginal way? Let's say I'm trying to debias only the gender, then it may have some adverse effect on skin color, or some other bias may come. So what should be the right approach to take care of this?
Yeah, that's a fantastic question, and there's no easy answer to this at all. And this is one of the things it's one of the big themes actually that's coming up now in the fairness literature over the past year or so, sort of this idea of like intersectionality, and the idea of debiasing along one dimension will potentially harm others. There is really just no easy way to deal with that. So this is something that it's sort of this idea of, I think as we start to discover more and more of these patterns, right, the tools are going to evolve to be more sort of deeper in how they think about, not just one domain, but maybe, thinking about 2, you're thinking about several, you're thinking about their intersection. And this is, and as the tools continue then to evolve in being, sort of visualizing more complex patterns of bias, at the same time, we're going to be discovering even more complex things. And so this is kind of part of the ongoing effort, and there's absolutely no easy answers to any of this. Yeah, but that's a really good point.
Thank you.
We have time for one more question, if somebody else. Okay, thanks a lot for your talk. It was really great hearing about this work.
It was great. Thanks very much for having me.
Yeah, thank you.